Welcome to this video in which we will be talking about Gaussian quadrature so that by the end of this video you will be able to calculate integrals using the Gaussian quadrature method. Now, up to this point, when we were talking about these Newton-Cotes methods, we have only used equally spaced subintervals. With one exception, the composite trapezoidal method had a formula initially that would be applicable to non-equally spaced subintervals as well. But every one of these other formulas that we then optimized assumed that the spacing between adjacent points was equal to a spacing of h. Now, the end result of those formulas, these Newton-Cotes formula, was a weighted sum of the data points. So there was a prefactor in front of some of these function values, a 4, for example, or a 2. Now, what we're going to do now is drop the requirement that points are equally spaced. Now, where shall we place the points, right, if we have choice? Or is there an optimal way to place the points? And that leads to the idea of Gaussian quadrature. So what we're going to do is we're going to approximate the integral from a to b of f of x dx by a weighted sum of the function values. Now, the weights are these c sub i's, and the points where we want to evaluate the function, those are called the Gauss points xi, and they now don't have to be equally spaced. So let's do an example for 2 points, n is equal to 2. So then we approximate the integral from a to b of f of x dx by the sum of c1 times f of x1 plus c2 times f of x2. Example for 3 points, well, you just have the sum of 3 function values at x1, x2, x3, each weighted with their own weight c1, c2, and c3. Now, we need to find these weights ci and the locations xi. But how? How do we do this? We want to have them be optimal. So let's require that if f of x has a special form, the Gaussian quadrature will be exact up to round-off error. Okay, so what are those special f of x? Well, let's use monomials. So f of x equal to x to the power 0, which is 1. Then the next one we want this formula to be exact for is f of x is equal to x to the power 1, then x to the power 2, x to the power 3, and so on. As many as possible. Okay. So if we have 2 points, then our number of unknowns is c1, c2, the 2 weights, and the 2 locations x1 and x2. And now we want to choose them in such a way that we get as many of these monomials calculated exactly up to round-off errors. To make things a little bit easier for now, let's assume that our integration bounds are a is equal to -1 and b is equal to +1. So we're always integrating between -1 and +1. Now, if that's not the case, then we'll have to do a coordinate transformation, but we'll talk about this later. So that means I want to have the integral from -1 to 1 of f of x dx, where f of x is equal to 1. Right? I want to be able to integrate this exactly. Okay, so I know that the integral from -1 to 1 of 1 dx analytically is equal to 2. So that's the analytically exact solution. And I want my Gaussian quadrature formula here to give me exactly this value of 2. So that means that c1 times f of x1, well, if f of x is equal to 1, then f of x1 has to be 1, as does f of x2 has to be equal to 1 as well. So the 2 has to be equal to c1 times 1 plus c2 times 1. Now, I want my formula to be exact as well for f of x equal to x. So let's do this integration from -1 to 1 of f of x dx equal to x. So integral from -1 to 1 of x dx, that's a half x squared between the bounds of -1 and 1, and that's equal to 0, right, if you plug in the integration bounds. Now my Gaussian quadrature formula is supposed to give me this exactly. So that's supposed to be equal to c1 times f of x1 is x1. So c1 times x1 plus c2 times f of x2, but f of x is equal to x. So plus c2 times x2. And I want to be exact as well for x cubed. Okay, so the integral from -1 to 1 of f of x dx, where f of x is x squared, is equal to 1/3 x cubed between -1 and 1. If you plug in the bounds, that's 2/3. And that's what my Gaussian quadrature formula is supposed to give me. So let's apply this. So that would be c1 times x1 squared plus c2 times x2 squared, right? Because the f of x is x squared. So up till now I have 3 equations, but I have a total of 4 unknowns, right? c1, c2, x1, x2. So I can actually force my Gaussian quadrature to be exact for one more monomial. So it can be exact as well for x cubed. So the integral from -1 to 1 of x cubed dx is 1/4 x to the power 4. And if we integrate that, that's 0. And that's what my Gaussian quadrature is supposed to give me. So that would be c1 times x1 cubed, because f of x is x cubed, plus c2 times x2 cubed. So now I have 4 equations for the 4 unknowns. Unfortunately, this is a nonlinear system, right? Because the unknowns c1, c2, and x1 and x2, the x1s and the x2s appear in nonlinear terms. So there will be multiple solutions. And let's require that the xi are symmetric around the middle of this integral. So the middle of the integral from -1 to 1 is at 0, which means if the x1 and the x2 have to be symmetric around 0, that would mean that x1 has to be minus x2. And if we add this additional requirement, we'll find a unique solution. And the solution is that the weights c1 and c2 are 1. And the 2 points x1 is -1 over the square root of 3. And then the second point x2 is +1 over the square root of 3. Okay, so that means that the integral from -1 to 1 of f of x dx is equal to, if I use 2 points, 1 times f of -1 over the square root of 3 plus, 1 times f of +1 over the square root of 3. Okay, and this formula is exact if f of x is equal to 1 or x squared or x cubed or any linear combination of them. So this formula is exact for polynomials up to order of 3. So let's do an example for this. Let's calculate the integral from -1 to 1 of the cosine of x dx. So the integral from -1 of the cosine of x, there's the dx missing here, is approximated by 2-point Gaussian quadrature as 1 times the cosine evaluated at -1 over the square root of 3 plus 1 times the function, which is the cosine, evaluated at 1 over the square root of 3. And if we plug these numbers in, we get this number here, 1.675823, and so on. Now, if we calculate the analytically exact answer for this, we'll find that this is 1.6829, and so on. And you'll see that our answer, just with 2 points here, is very close to the analytically exact answer. Now, we can improve on this result by using more Gauss points, not just 2. So for example, if we were to use 3 Gaussian points, then the answer would be for the integral 1.6828. So if you compare that to the analytically exact answer, 1.6829 versus 1.6828, you see that gets even closer to the analytically exact answer. And in fact, we can add more and more points to the Gaussian quadrature formula. And in order to do this, we need to know where are the points located and what are the corresponding weights. And they are shown here from the source from Wikipedia, what the analytical formulas for the points and the weights are. Now, the textbook has a table like this as well, but unfortunately, they do not give you the analytically exact formula for the points or the weights. Instead, they don't even give you the numerical values up to double precision. So do not use the values from the table in the book, but please instead use this table, which you can evaluate up to double precision or any finite precision that you like, because you're given here the analytical form of the Gaussian points, xj, and the weights. Now, what do we have to do if the interval of the integral is not from -1 to 1? Well, then we have to do coordinate transformation. And the coordinate transformation to go from x to a coordinate t would be x is equal to 1/2 the t times b minus a plus b. So if x goes from a to b, right, then t will go from -1 to 1. Okay, so now if we take the differential, the dx is equal to 1/2 b minus a dt. And if we use this definition in the original integral from a to b of f of x dx, we can coordinate transform this into an integral from -1 to 1 in dt, where now instead of evaluating at f of x, we have to evaluate this at, well, x is equal to 1/2 t b minus a plus b. Right? That's where we have to evaluate the function f. And then from the dx, we'll get 1/2 times 1/2 b minus a. Okay, so that would be the formula then to use. You'd see that the integral right from a to b, right, this a here, that's the a that appears in the formula over here and there at the end. And the upper part, at the upper bound of the integral, this b appears in the formula here, here, and here at 3 individual spots. Or, right, if you prefer to keep the variable names for the quadrature points after transformation as x as they appear in the table, right, this is the same formula, now just written with x in here in the right-hand side that goes from -1 to 1, which then gets replaced by the Gaussian quadrature sum with the weights ci and xi, and the ci and the xi, they come from the table from the previous slide. Okay, so let's do an example. Let's calculate the integral from 1 to 2 of the sine of x dx using 3-point Gaussian quadrature. So let's start with a, identifying what a is. Well, a is 1 and b is 2. Okay, and let's write then the integral from 1 to 2 of the sine of x dx is equal to, so here is the formula. Let me mark what I have determined so far. So I know that my a is 1, so that's this value over here. And I've determined that my b is 2. That's this guy. So that goes into the formula over here. And I'm using 3-point quadrature. So 3 points, which would mean that 3 points. So I would have the sum. Well, let's actually use this formula here. So b minus a over 2. So 2 minus 1 divided by 2 times the sum. I equal 1 to 3. Right, that's m is equal to 3. 3-point quadrature, sum of 1 to 3. Of what? Well, of the ci, the c sub I times f evaluated where? Well, b minus a, so 2 minus 1 divided by 2 times xi plus 1 plus 2 divided by 2. Okay, so let's 2 minus 1 divided by 2 is 1/2. And then we have 3-point quadrature. So number of points here is 3. So that's what we have to look at. Let me grab this color here. And now, right, Ci, the first weight, doesn't matter which order we do this. We can go in increasing values of x, or let's do that, increasing values of x. So I'm going to start here with the minus the square root of 3/5 for x, and the weight then is 5/9. So this would be here 5/9 times f evaluated at, well, the f is the sign, so let me write this directly. So the sine of 2 minus 1/2, that's 1/2, times the x of this. So let me mark here the x, right, as this guy. So that would be negative the square root of 3/5 plus 3/2, right, 1 plus 2/2. So that's this one. Let's open here a square bracket and make this into this. And then the next term, the second point, is plus the weight now is 8/9. So plus 8/9 times the sine of 1/2 times the point location, which is 0. 0 plus 3/2. Okay. And then we have plus the last weight is again 5/9 times the sine of 1/2 times the x location, that's plus the square root of 3/5, plus 3/2. Okay, and then square bracket closed. And if we type those values into the calculator, we get 0.95644963343. Now, the exact answer, right, the exact answer for this would be the integral from 1 to t2 of the sine of x dx. That would be minus the cosine of x between 1 and 2. So that's equal to minus the cosine of 2 plus the cosine of 1. And if we have those values, that would be 0.9564491,424, and so on. So what we'll have to do here now is compare this value against this value. So let's calculate the true relative error. Okay, so that was true relative error definition was the true solution minus the numerical solution divided by the true solution. So if we plug in those values, what we'll find is that the true relative error is negative 5.1338 and so on, times 10 to the negative 7. So 10 to the negative 7. So just using 3 points, we get a very accurate estimation for this integral, which makes Gaussian quadrature really powerful because it is quite accurate. Okay, now we can further improve this by doing a composite version of Gaussian quadrature, right? Applying this to subintervals. And that would just require us to apply the coordinate transformation to each subinterval. So the general idea of the composite was that we split the overall integral into the sum over n subintervals, right? Doing the integral over each subinterval from xi to xi plus 1, which then with the coordinate transformation to convert this integral from xi to xi plus 1 to an integral from -1 to 1 is just using the general coordinate transformation formula, right? Where b is equal to xi plus 1 and a is equal to xi. Now, if the Right, here's the lower bound, there's the upper bound. If the subintervals are equally sized, then xi plus 1 minus xi is equal to h. So I can substitute that into here, right, using just h in the evaluation of f and the integrals. And now we apply for this integral from -1 to 1 the Gaussian quadrature formula. If we use m points there, then we have two nested sums. We have the outer sum for the subintervals, and we have the inner sum over the Gaussian quadrature points. And then for reference, here is again the table. Thank you for watching.